Excellent. On this very important flux capacitor part out of stainless steel, all that's left is to notch out this corner. This will be a piece of cake with 4mm carbide end mill. Just take it in one pass and we'll be done and can ship this part so Doc Brown can go back in time. Excellent. A quick deburr and it can go off to the customer. That went marvelous. Hey, welcome back. If you ever had to mill stainless steel or other sheet metal on a manual milling machine and you tried an approach like I just showed in this very dramatic recreation, you might have seen a very similar result. A lot of heat, a lot of smoke if you're, for example, using a piece of wood backing plate, an absurd amount of burr, and the tool life is very bad. So I learned this the hard way too. I burned up a lot of cutters doing sheet metal work on milling machines because often really sheet metal tools were either not available or we needed a higher precision on certain parts. So we went for milling. This is true for both CNC and manual milling. This didn't burn and burr up because my speeds and feeds were off. These were very reasonable speeds. 2000 RPM with 4mm 4-flute carbide end mill, which is suitable for stainless steel, but still the result is not very nice. And today I want to show you a few tricks or the main strategy that I picked up over the years to do extremely reliable sheet metal milling, both on a manual machine and on the CNC milling machine. And especially for the CNC machine, if you run a machine with very high speed spindle, I will give you some outline for speeds and feeds that will work always. I have used them countless times and I've given them as a recommendation to people countless times, and the feedback always was like, ooh, that worked. So first, let's start by looking at what happened here on this smoke machine. The overall setup is all okay. We're clamped down with 3 strap clamps. We have a back fence so that our part is straight. We have a wooden backer plate. You can use something different here too. Wood is fine in my book. Wood or a piece of phenolic, fiber reinforced phenolic is also nice for a backing plate. I wouldn't use plastic because when it melts it gets a real mess. For real precision work, a piece of precision aluminum plate is nice, like the two-sided parallel milled material. That's a nice backer, but something for if you need, for example, to make an enclosure and need some precise cutouts and a few hole patterns, a piece of plywood is absolutely fine. The cutter I'm using is another topic. Don't go too big on the cutter with sheet metal. The bigger the cutter, the more trouble you will get. It will start to vibrate. This is 2mm thick stainless. It's relatively stiff for the size of piece of material, but it's only stiff within reason. If we tried to, we can use a cutter like this on here and do a small cutout, for example, if we need the large radius and we don't have access to a CNC mill, then we can use a cutter like this to create a cutout. But in general, this is better done with a small end mill. Don't be scared of smallish end mills. A 4mm end mill can do a lot of work and give you great value for relatively little money. So sheet metal from a certain material, like in this case 14301 stainless steel, behaves very different in a sheet form than say round stock or flat bar. The sheet metal from the rolling process has very different properties and therefore machines very differently, as you can see here by the ginormous burr created and the heat created. The The huge smoke cloud that we made was the heat from the cutter burning the plywood, of course. So a full slotting approach in sheet metal is often the worst case that you can try to achieve. What works, in my experience, the best is to use a high-speed approach. We max out the spindle of the machine, in this case 2000 RPM, and we feed very fast, but with a very low depth of cut. Yes, this will take longer, but also it will, first of all, yield a nice result, and also the cutter will last longer, and it's overall just a nice result. So let me show you the general technique. Since I don't want to waste a whole lot of sheet metal for this demonstration, we're just going to take another bite at this cutout. For this to work, it's good to have good layout lines. So let's say it's a good idea to lay it out. I'm using the DRO now. Then I'm just touching off in C on the sheet metal, and then I will take 0.1 millimeter deep cuts relatively fast. Let me demonstrate. Okay, I went down 1.8 millimeters in 0.2 millimeter increments. I noticed that it's working quite well, and so I stepped up my depth of cut. And now I have 0.2 millimeters left, and I will overfeed this. I will go down to 2.5 millimeters. So I'm cutting into my waste board, into the spoil board below the sheet metal. And this approach gave me an extremely clean cutout. And this approach gave me a very clean edge with almost no burr. There is a little bit of burr, of course. This will knock off very quickly with a file, or if you feel very fancy with a deburr end mill. But even the sidewall is very clean. This low depth of cut, very high feed approach comes more or less from the CNC world. It's a high-speed strategy, but it works on a manual machine just as nicely. And this approach it's very useful to cut sheet metal, but it's also useful to cut other things. It can be used to cut hardened materials very effectively with a very good cutter life. It can be used for sheet metal. It can be used for if your setup is very flimsy. If you have a very light duty hobby machine like a Seek mini mill or something like that, or a Seek X2, this approach works very well. This usually works better than trying to do a large depth of cut and a small step over on a soft machine. Like many people do adaptive strategy with a very high depth of cut and small step over. That's a different high-speed strategy, which requires a little bit of a stiffer machine. Low depth of cut, high feed works better on soft machines in my experience. We can do one step better. Let's say we want the edge to be a little bit cleaner, then we would do the slotting, the high-speed slotting with a little bit of material allowance, like 0.2 or 0.3 millimeters, and then we take a climb milling past it full depth to clean it up completely. As you can see, when I blow the chips away. So when I take a screwdriver, you can see the reflection from the screwdriver blade and the sidewall finish of the sheet metal, and that should give you a good idea of how good the surface finish here really is. And yeah, it's sheet metal, and we cut it dry, and the cutter will last forever doing this. I've done this on the CNC machines in general to great extent, and even in overnight runs, and it's just working. Each time I try to do a high depth of cut approach on sheet metal, it ended in tears. Okay, another view at the cut we just took. As you can see with the screwdriver again, there is quite the okay surface finish, especially considering that it's just sheet metal and not a particular high quality material. And if anything, just the nature of the quick deburr necessary for a cut like this is worth the extra effort in my mind. Yes, it takes a little bit longer, but also you're not dealing with a burr that's just annoyingly big to be removed. Different machine. This is the CNC router or CNC mill, and I just used the same technique. Very small depth of cut, but rather high feed. In this case, I was spinning the cutter at 12,000 RPM and feeding at 1500 millimeters per minute. And the result is basically the same. We better get a rather clean and very process reliable cut. But you might notice that there is quite a nasty burr here. And this happened at the very first pass. As you can see here in the replay, when the cutter took the first pass, it went rather deep into the material. That's just caused by the matter that sheet metal especially when you clamp it on a piece of plywood, is rather unflat. It's not parallel to the ways of the machine. So I would recommend to start above the material, like 0.1 or 0.2 millimeters is enough in most cases. Then you just take air cuts until you reach the material, and then you will start out with burr-free cut. Also, another thing that you might notice, there is this little clamp holding the cutoff. That's kind of an important piece of the puzzle when you do this on a CNC machine, because if you don't clamp the waste down, you do not know what the waste will do. It often tends to, on the very last pass, to fold up, and then the cutter kind of catches it. Or sometimes, even funnier, the cutoff gets flung onto the remaining material, preferably in an area where the cutter will next plunge down and bore a hole. Then you have to then you have a real problem. Then the cutter will try to plunge down into this loose piece of stock. So either machine it away completely, make it entirely into chips. That's my preferred method on internal cutouts, or clamp the stock down if it's just like one piece that you're removing. For work holding, as I said, clamps are fine if the part is not too big. Double-sided tape, super glue works extremely well. I have shown that in the past for sheet metal. So all these methods work. Let's flip it around and do another try with the CNC with starting to cut in the air. So you see that we can get a burr-free result. Second try with starting in the air, and by the tool marks you saw that the material was far from flat. That's two reasons. First of all, the plywood subplate here is not very flat to begin with. Secondly, it's soft, so if you clamp it in two places it wants to deform. And thirdly, the thin sheet metal, when you clamp it down, also wants to bow up, especially if you're clamping down on a soft material. But this gives us a very burr-free result that I'm not crazy careful to touch without cutting myself. So that's the reason why I prefer the strategy for sheet metal. And on a CNC machine you usually get away without doing a finishing pass, a finishing clamp pass, because the machines are repeatable enough so the individual step-down cuts blend nicely. I want to talk about the cutter later, because there is one important thing about the cutters. You don't need to buy a very expensive cutter for this technique. Any old cheap carbide end mill will do, but you have to look for one thing if you want to do this, which makes this technique so much better than with different end mills. You will see. We have two carbide end mills here. They're not the same diameter, but that doesn't matter for what I want to show you. Approximately the same helix angle, same flute count, but there is a tiny difference. When you look at the end of where the spiral flute meets the front cutting edge, this end mill here on the right, it has a sharp edge, and this one has ever so slightly of a chamfer. This edge chamfer makes this technique with a small depth of cut and a high feed so plausible and so well working. And as long as you stay within the width of this corner chamfer, the cutter will last forever if you do this approach. And you will not really wear the end of the end mill. You can get several hours in the cut out of an end mill with this technique and this approach without a problem. So if you want to do a cutting approach in sheet metal like I demonstrated, whatever you do, try to get an end mill with either an edge chamfer like this one or an edge radius. In my experience, the edge chamfer works better. The edge radius tend to put a little bit more axial force into the part than is really necessary for cutting sheet metal. So try to get one that has an edge chamfer. Why does the chamfered corner of the end mill help us with cutting sheet metal with this high speed, high feed approach? Well, I have drawn two end mills here, center line. This one has a sharp corner and this is a chamfered corner one. Green is the material, and I have drawn in a block of material. The length here, the distance here, is feet per tooth. And on a 90-degree end mill, that equals the thickness of the chip. It's just how much material it removes per tooth, per rotation. And when you measure that, that's the chip thickness. When we go over here with the same feet per tooth, it feeds the same distance here, but when we measure the thickness, like this, the chip gets thinner. Over here we have like 10 millimeters, and over here it's substantially less. It's only like 7. Means we could feed this end mill way faster than we can this end mill to get to the same chip thickness. Also, second effect, a 90-degree corner is more prone to chip away because it's a sharp corner than a 135-degree corner on a chamfered end mill. There is way more material backing it from behind, making it more resistant against chip out or general abrasive wear too. So that's the two reasons why the chamfered corner end mill works very well for this technique. And a third general benefit of this process with a very shallow depth of cut and a high feed is the end mill has spiral flutes. And these flutes, when the tool spins, tend to pull the work upwards away from your work holding. And the more flutes that are engaged, the more of the pulling force you get. And the result is vibration and burrs and just a whole mess. So if we keep the depth of cut extremely small, the effect of the spiral is almost neglectable. So that's the main secret behind this technique. Chamfered corner end mill and the very shallow depth of cut for minimal axial forces. So when we look here in the catalog, and the corner chamfers on these cutters, for example, start at 1 millimeter. Below 1 millimeter, they are sharp cornered. So that's something you have to look in your tooling catalog or get the information from your tooling supplier if you want to try or if you want to benefit from this technique. In general, the corner chamfer end mills are a little bit more robust, especially when you do steel and stainless. So I hope you enjoyed. I hope this is somewhat helpful. I often see problems when people try to mill mild steel or stainless steel sheet metal, and It gets all nasty and burned and just not very nice. So might be worth to try it this way. Thank you all for watching, and I'll be back.